Hey, and today we're going to be discussing the RSA public key algorithm. Now, this is going to work off something called Euler's Totient theorem. Now, that looks a little bit like this. T raised to the power of phi r equals 1 with a modulus of r. Now, two things might look a little foreign here. Phi and modulus. So let's examine those. Phi is a function that counts up all the numbers between r and 0 that are relatively prime to r. So, the function for phi would be dependent upon the factors that make up r, based upon the fundamental theorem of arithmetic that r is made up of a set of prime factors multiplied by each other to obtain r. So, to get these numbers, what we'll do is say phi r equals r times 1 minus 1 over the first factor of r, multiplied by 1 minus 1 over the second factor of r, and so on until the nth factor of r. Now what this does is essentially take the number of digits between r and 0, and r amount of digits, and multiply them by 1 minus 1 over each of r's factors. Now, what this will do is essentially say, say r has a factor of 2 in there. Now that means that 1 minus 1 over 2 is a half, r times a half means that we have half of r. So what that means is that from 0 to r, every 2 digits there will be a digit divisible by 2. So take out half the digits. That's what this equation will do. And so on with each of the factors. Takes out a third with 3, takes out a fourth with 4, so on and so forth. So then we have modulus, which is essentially known as clock-facing arithmetic. So with modulus, what we have is, say if we have 1 with a modulus of r, as we did before, that's equivalent to 1 plus kr. Essentially, modulus rotates the r into the 1 a k amount of time. So k is any integer. It essentially says that 1 can be essentially 1 plus any multiple of r. So, if r was, say, 16, then it would be, 1 could be, 1, or 17, or, say, 33. So, that's what modulus does. Anyway, so, back to Euler's Totient theorem. Now, t raised to the phi of r, remember that's going to count up the relatively prime factors, equals 1 with a modulus of r. Now, notice that we can square this. So if we were to square this, that would mean that this we can multiply by 2, since it is already an exponent, and 1 to the modulus of r would be squared. Now, notice the factoring that will happen here. This is two numbers, 1 and modulus of r, 1 plus kr. So when we square that, it becomes 1 plus 2kr plus a kr amount of kr. Now, there was a reason that we have a kr amount of kr. It's because k can already be any integer, and since we have just simple multiples of k here, what's going to happen is they're all going to be devoured into the modulus arithmetic. So when we take all this and put it in the same place, we get 1 plus 2 plus kr as a coefficient of kr. That gets divided into that. We have 1 with a modulus of r once again. Now, notice this side hasn't changed, this side has. We can do it as many times as we like and come up with a new equation. T raised to the k phi r equals 1 with a modulus of r. That's k. K implies more modulus arithmetic. So that means we have t to the 0 with a modulus of phi r equals 1 with a modulus of r. Now, for future purposes, we're going to substitute out 0 with modulus of phi r for s. Now, that means that we have t to the s equals 1 with a modulus of r. That 1 there isn't of much use to us. The way that we're going to get rid of that is multiplying both sides by a t. So, that means that when we multiply both sides by a t, what we're going to end up with is t to the s plus 1 equals t with a modulus of r. since 1 with modulus of r is 1 plus kr, multiply 1 by t, you get t, multiply modulus of r by t, you still get the modulus of r. T is an integer. So we end up with this equation. This is going to be useful later. Now, note the s plus 1 in the top. We're going to make that equivalent to p times q, which will help us in our public key. So p times q equals s plus 1. Now, let's substitute out the s for what we had before. 0 with a modulus of phi r, you add a 1, and that becomes p times q equals 1 with a modulus of phi r. Now, the reason that this is going to work out for us is because we had an equation earlier where we had 1 with a modulus of phi r, and that was t to the 1 mod phi r equals t with a modulus of r. So now once we substitute these in, we end up with t to the pq equals t with a modulus of r. We're going to split that up into two equations. Now notice that it's t to the p times q. What that means is that we can separate it, which means t to the p raised to the q equals t with a modulus of r. Split that, we get t to the p equals x with a modulus of r. We're going to make that an intermediate term for us. And then we take the x and raise to q, and we get t with a modulus of r. Let's see, it's because we have t on one side, 2 on the other. Follow it start to end, and you get these equations. Now, these are going to be helpful when we move on to the RSA arithmetic and explanation.